Another example, which is very popular, it was designed by a very gifted chemist called Roessler, who was classically trained. He reads Greek literature, etc. And this is Germany, where they still have classical education, or used to when he was young. And this system is supposed to explain how you make toffee, you know, when you go to amusement park, how you mix this thing that then you can eat as candy. And with reasoning, which please read in the book, some explanation of it, Roessler designed 3 equations which capture essential features of Lorentz flow, but are simpler to analyze than Lorentz flow. So there are 3 variables, and there are 3 parameters, and the system is nonlinear because there is this combination here, which makes it bilinear or second order in the variables. And again, you put this thing on a computer, and as it's always true of equations, but nobody, you know, the real truth about equations, you have no idea what solutions. When you look at these equations here, given to you by Roessler, they're simple. They can be derived on simple phenomenological grounds, but you have no idea what the long-term behavior of this is. So put it on a computer, as you will do, and you discover that the thing does something like this. It goes up, it falls down, it goes up, it falls down, it goes up, it falls down. And it seems to do this forever. As a matter of fact, we cannot prove mathematically in this case that it does it forever, but for this particular values of parameter, the system seems to be never approaching any limit cycle. It just has this behavior. So that's the simplest example of differential equations that exhibit what we'll call chaotic dynamics. The previous one of the 3-disc billiard was the simplest example of maps that exhibited. And now I've told you, whenever you have a dynamical systems, the first thing you should do, if I haven't told you before, I tell it to you now, the first thing you should do in a dynamical systems, you should solve for equilibria, which means you should set left-hand side 0 of this equation to 0, and solve for the places where velocity field is 0, so you don't go any place, you stay there forever. They're called equilibria. When you do this, and you will do it, it's easy to do, you discover that this system equation is bilinear, so it can be made to look quadratic. This system has 2 equilibria. There is one here, one here, and there is another one here. So this is lower equilibrium, upper equilibrium. And nothing happens at them because they're stable, but you notice that in their neighborhoods seem to care about them. So they play some role. It'll turn out they play a very crucial role, as we'll show, in shaping the dynamics. And it turns out this equilibrium has to do with swirling the points around. So trajectories swirl around. And this equilibrium turns out to define the basin of attraction. So there is some kind of wall here that contains this point. And everybody who is close to this point, but on this side of the wall, falls into the attractor. And everybody who is away falls away. So this is actually the border of the basin. So in this very trivial example, you see already intuitively that equilibria might play 2 important roles. So one is it shapes the flow, and the other one is it separates the things that belong to a tractor from things that run away. And this seems to be an example of what I told you was called strange attractor. You run it. This is run for some time. There are arbitrary units, but eventually you understand how to get a unit of time. So eventually you will see that some units that you'll learn how to interpret. For time as long as we want, this never settles down. So that's our working example of strange attractor.